welcome back to my channel. Today I'm going to walk you through my Bigram GPT model. So yeah, I will be explaining the code path, like codes which I have changed and which is a little bit different from Android source by a GPT model. And to understand in a depth way of each code which I have written, you can go to his channel and see this video. This link I will be providing in the description. So if you see this video of his, so this is an ad, so let's just leave it aside, right? So now let me proceed. So the reference, I would say, it's from Zero to Hero video on GPT, which is available over here. So let's just skip it out. And he has explained each and every code blocks and code chunks which I have which is over here. So first, this is the notebook which he has provided, and I will be explaining some part of my codes which are available over here. This is the Bigram GPT model and the full finished code for reference he has given. And then and then we can see that after this, yeah, so this is the model and what additions I have made to this to this Google Colab notebook. Basically the additions which I have made is I have made a pickle model basically. So what does this pickle model do? So basically this pickle model is going to help you to get the implement the GPT model or Bigram GPT model in different platforms like app, web. Okay, so for implementation purpose I have made the pickle model, and I have also added a GPT model, extra GPT model of my own with mine, like whatever I understood from his video. So I would recommend you to see his video. It's like a great thing. He's a great guy. And then I have also added a bigram model, extra bigram model. So I'll be explaining each and everything step by step. So first let's start with his Google Colab, and then I'll come with my Kaggle notebook and explain what additions I have done. So let's start. So basically what we're doing first is we always start with the data set, right? So what we're doing, we are using this, basically this we get is used to get the data set from the some link we provide or from the GitHub link. So this is the data set we have. So let me just open this data set and show you what's this data set. So what data set are we downloading? We always start with the data set to train on. Let's download the tiny Shakespeare data set first, and here we are downloading the tiny Shakespeare data set. Now let me show you what this link. So this is the data set. So you can see it's a very big one. So 1 million characters are there almost over here, and it's a 1 MB file. We can say 1.06 million. Oh, that's great. Now what we do, we read it in to inspected. So we open that, like we open. So let me, okay, it's showing I'm not authorized. Oh, nice. So what we do, we open the input.txt file and we encode it. Yeah, you know, right? UTF-8 or some block, like encode it, and then we read the file. So let me show you over here. Yeah, right, we open it and we read the file, and now let's look at the first 1,000 characters in the data set. So what we do after reading it, we print the length of the data set. So you can see here he has done, oh yeah, here he prints the length of the data set. The length of the data set in characters is this much, that is around 1 million, you can say, or we can say whatever is provided here. Now let's look at the first 1,000 characters. So this is the first thousand, we are printing the first 1,000 characters in the data set. So this is the first 1,000 characters in the data set, you can see over here. Now when I just, yeah, now when I just go, like, these are the first 1,000 characters. Then here all the unique characters that occur in this set, all these unique characters which occur in the set, first what we do, first we set it to a text. Okay, we set all the text and then we list it out, like we make a list of this set of text, and then we sort it out, right? Then we sort it out. After sorting it out, we initialize it to a variable called characters, and this or chars, and this length of this chars is the vocabulary size. Then we concatenate with join dot characters, and then we print the vocab size. So what is the vocabulary size? The length of this character. So what is the length of this character? 65. As you can see, this is the all the required things. Now what we do next is we create a mapping from characters to integers. So here basically this is the character. Ch stands for character and this I stands for integer. Now for each I or ch we enumerate the characters, right? So this is basically encoder decoder performance. What does the encoder do? Encoder take a string and output a list of integers. What does the decoder do? Decoder takes a list of integer and gives output a string, right? So what we do here, first we print the encoded version of hide there. Now you can see here there's a space, right? So this space is printed as 1, as I hope so you notice over here, and the other things are the integers that are converted, right? Then what we do is we decode it. We decode this part, and when we decode this part we get it as hide there. So this is basically the performance of the encoder and the decoder over here, and the mapping. Now let's now encode the entire text data set. This was just a chunk of data set which we encoded, right? That is, we encoded high there, and then we printed the decode and encode version then we printed the decode version of the encoded version. Now let's now encode the entire text data set and store it into a torch.sensor file, right? So for that we use pytorch, right? Now what is this PyTorch? Let me just show you the website. How does it look? So this is basically a PyTorch website. So what did we take from here? We used the PyTorch. We first import the torch. From here, what is needed for us? We are storing the data set into the torch.tensor. So here we are storing the data set which is encoding the text. Here we encode the text and we store the data set in the torch.tensor, and this whole thing is stored in a initialization called data. Now then we print the data.shape and data.dtype. So what is the data.shape? The torch.size is, as we saw, 1 million, and the data torch is int 64, that is, as we saw, 65 over here, like this is the 65 over here, so it's the int 64 over here, we can see. Next we print the data, like the 1,000 characters we looked at earlier. Which one? These characters, we print these characters in the integer, right? So this is what it looks. The zeros are for the spacings, like the next letter, like this, and the one are for the spacing between the characters. Now let's proceed. Yeah, let's now split up the data into train and validation sets. So what does this do? This takes the first 90% that will be trained, and rest are the validations. So this will take the first 90% and it will train the data, right, of first 90%. So we use, you can see, right? Yeah. Next we validate the data of the next 10% of that. Now we initialize a block size, that is 8, and we train the data of 9 elements. Block size plus 1, that is 9. So you can see here 18, 47, 56, 57, 58, 1, 15, 47, 58. These are the tensor values of this, right? So how many are here? So block size 9 blocks are there, you can see, right? Now block size is 8, but we have taken 9 to train data, 9 sets. Now what we do is we initialize x and y. Now what does this x and y initialize? This the first x is initialized with the train data and the block size we had, and y is initialized with the train data with having a 1 before that and the block size first plus 1. Then we put a for loop on it and we get the output like this. What is the output? When the input of tensor is, when the 18 is the input, the target is 47. When 18 comma 47 is the input, the target is 56. Basically it's just printing this part, this one, in a, like, where what, when the input is what and where the target goes, and the final will be 58 obviously. Now what we're going to do is we're going to do a torch manual seed on it. So this we have initialized to 1337. Now the batch size is 4. What is the batch size? How many independent sequence we will we process in parallel? And what is the block size? That is 8. What is the maximum context length of the prediction? Next, we make a function called def get batch split. So it will split the listen. So we generate a small batch of data of inputs x and targets y. The input is x and the target is y. The data, like train data, if split is train, else validate the data. If the split contains this train, then we will split it. Otherwise, we will validate the data. Now ix, this is torch. So it will just take the length of the data minus the block size, comma the batch size whatever we have taken. Then we initialize x and y, and then we return this both. We can for an, I again repeat, for better understanding of it, you can see the video of Andres Carpathi's, so you can understand full-fledged thing in a better way. Now what we do, we return x comma y. What is x over there? X is the torch, and we are storing in a stack, right? What we are storing in the stack? We are storing the block size from I to ix. Here the data is I is to I plus block size, but in y the data is I plus 1 is to I plus block size plus 1, and this is stored in a stack, right? Now now what we do, first we take xb and yb, that is equal to the get batch of train. So here we have split, we have written over here, the split is nothing but over here is train. So when split is equal to train, then these things occur, right? So here first we print the input, then the what is the print the input, xb dot shape we print in that banner, and then we print the xb. Next we print the targets, then we print yb dot shape, and then we print the yb. Then we take, like, you just slash 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 slash. So let me first explain you this part. So what we are printing first, we are printing the input. Now the what are the inputs we are printing? Xb dot size shape. So we are printing the size of it. The size of it is torch dot size 4 comma 8, right? 4 comma 8. So we are printing the batch size and the block size number over here. Then what we are doing, we are printing the xb. Now what does this xb prints? This prints the integers. So what are the integers it prints? 24, 43, 58, 5, 57, 1, 46. It prints all the integers. And then what does the target do? Same, the target first prints the yb dot shape, that is the batch size and the block size, and then the tensor, like the yb whatever we have stored in that stack. So these are the both the stack stored integers. Now next, similarly like we did for here, when the input is this, then the output is this, when the input is this, then output is this, target is this. Similar, in the similar way we put a for loop. So for b in range of batch size, that is the batch dimension, then for t in range of block size, that is the time dimension, the context is equals to xb b t plus 1, and target is equals to yb b comma t. So here when the input is the context dot to list, we format it, the target is this target, right? Now let me see what does it happen. So when the input is 24, when we are taking 24 as the input, the target is 43. When the input is 24 comma 43, the target is 58. When the input is 24 comma 43 comma 58 comma 5, the target is 57. When the input is 24 comma 43 comma 58 comma 5 comma 57, the target is 1. Similarly it happens still till that 44, like the last part 44 comes, right? Till the 44, when the input is 40, sorry, it happens till the 43, right? So the last part here 43. So when the input is 24 comma 43 comma 58 comma 5 comma 57 comma 1 comma 46, the target is 39. Now how, where did this 31 come from? See, 24, 43, 58, 5, 57, 1, 46, 53 is one sequence. Then the final target, again this sequence is printed over here, where 24 is taken as input and 39 is the target. So the target is, final target is 39. Like that we do for each and every set. Whatever we got here, 1 2 3 4, like final answer will be 39 again. You can see how 39 came again, you would have doubt. See, right? So like this happens. Now what does it do? here it print the xb, that is our input to the transformer. This is our input to the transformer, right? What is transformer, why we use that, everything's available in this. Okay, and you can, oh yeah, over here I can just show you one of his playlist, which is very useful, the neural network 0 to hero. This is a very good playlist. You can just go through this every and each and everything of this playlist, and you can understand what is neural network. This just helped me out a lot in making my Bigram GPT model which I have made. So yeah, finally we come with the Bigram model, right? This is the Bigram language model. So yeah, let me just explain you the Bigram language model. So yeah, final output what will you get is, this is the whole thing, right? Here I have added every each and everything that we saw is been added over here with some hyper parameters, full finished code for reference, or you may want directly, you can go to the GitHub repo of him and we can see these things now. Okay, now as we were going side by side, so let's go side by side. So where were we? Yeah, so we were here. So yeah, first I'm importing torch, then I'm importing torch.nn has nn, then from torch.nn I'm importing a functional called f, and torch manual seed is 1337 as we did here. Now I am making a class that is a bigram language model which has in something taken from this nn dot module, right? So here first we are making a function that is self and the vocab size. Now what does this do? Each token directly reads off the logics for the next token from a lookup table. From the lookup table, where was the lookup table? If you remember, there was a lookup table we did, right? uh, yeah, this one, like this, something lookup table. So from the lookup table it will just take the token, and then we make another, like, another function called def forward and another function called def generate, which will generate the self, the id, and the max new tokens whatever we have. So first let's go through this function. So the idx and the targets are both b comma t tensors of integer, and the logist self dot token embedding table, that is idx, that is b comma t comma c, which we are taking. Now if the target is none, the loss is none, right? That if there is no target, then the loss is also zero. Now else btc, that we are taking three symbols, right? Btc. So what does this btc do? It logits dot shape, and these logits are nothing but it is the view of b cross t comma c, right? It's a view of b cross t comma c, and the target is the view of targets dot view b cross t, and the loss is equals to f dot cross entropy of logist comma targets. Next we generate, how we generate? Self idx max new tokens, these are the things used for the generating. So the idx is a p comma t array of indices in the current context. Now we put a for loop in range of the maximum new tokens, and we get the predictions, that is logist loss is equal to self idx, and we focus only on the last time step, that is logist is equal to logits, that is -1, that becomes b comma c. So here the last time stamp we took, so that becomes b comma c, and then we do a props, like we this is a logits, then this is a probability of what probability we take, f dot softmax logist comma dimension is -1. Here hashtag b comma c, we apply softmax to get the probabilities. Now sample from the distribution, we take the sample from the distribution. So before I proceed, I would recommend you to have some knowledge about probability and statistics, which we use here. Next we take a multinomial, like binomial. Then we have Poisson distribution, like that we have multinomial is nothing but the mixture of binomial and the Poisson distribution, right? So idx next is equals to torch dot multinomial we are using the probability prob comma num sample equal to 1. So what happens here, the c is replaced by 1, you can see here, that is becoming b comma 1. Next we append the sample index to the running sequence. We append the sample index to the we cat it, so we get b comma t plus 1, and finally we return this idx. Now m is equals to bigram language model, that is this whole class model in vocabulary size. Here we take the vocab size, or we can say the vocabulary size. Now, what is vocabulary size? I have explained here somewhere that vocabulary size is the length of the characters. What is characters? Characters nothing but the sorted list. Okay, the sorted list of this 1000 text. Now let's come down, come down, come down, come down. Yeah. Now we take the logis and the loss, that is equals to mxb comma yb. Next we print the logis dot shape and we print the loss. So what is the logis dot shape one? Torch size is 32 comma 65. It says that the size of the torch is 32 comma 65 and the loss is 4.8786. This is the loss, and the loss is n loss is backward, right? Next we see some decode. We decode these things and we get this, right? Next we create a pytorch optimizer. So what does this do? This optimizes our code properly. So optimizer equals to torch.optim, and when we put some parameters, and lr is equals to 1e minus 0. Here we uh, keep the batch size as 32, and for steps in range 100, increase number of steps for, we increase the if we increase the number of steps, the result would be good. So increase number of steps for good result. Next we take a sample of, or a sample, a batch of data is xb comma yb. We get the data from the train, right? Next we evaluate the loss. Here we this code evaluates the loss, and we print the loss dot item. How many loss? What is the loss dot item value? 4.656 3057 8. This one is the loss. Then we decode this, right? After decoding this whole code, we get this. How many max new token did we take? We took 500 max new tokens. Now the mathematical trick in self attention. So this is some mathematical tricks for the self attentions. This is a toy example, okay, illustrating how matrix multiplication can be used for weighted aggregation. If there is a weighted aggregation, how can we use a matrix multiplication method? So here it does the matrix multiplication method over here, where we take torch manual sheet 42, and here we do this thing, right? A is equals to this much, b is equals to this much, and c is equals to this much. Now consider the following toy example, like this following toy example. What do we get? B comma t comma c. B is the batch, t is the time, and channel we get it as 4 comma 8 comma 2. We like keep it as 4 comma 8 comma 2, and then we do x dot shape, so we get torch size as 4 comma 8 comma 2. Now we want x b comma t is equals to mean, right? Mean of I less than equal to t, that is x b comma I. So we do that, and finally if we use some version, right? So for b in range b, for t in range t, we take the x previous, that is x b comma, that is the t comma c part, and then we take the mean, that is x previous comma 0. Now what we do is we take a version 2, that is using matrix multiply for a weighted aggregation. Here matrix is multiplied for a weighted aggregation, then we torch all close. Here we get a, what to say, true or false answer, right? Boolean answer we get. Then we use a soft max and we get a true. Similarly we do another, that is version, this is a version 2, this is a version 3, and this is the version 4. This is a self attention version. Similarly, let's see a single head perform self-attention. Here we do a single head perform self-attention where the head size is 16. Key, query, and value we take nn linear, and k is equals to key and q is equals to query, and then we transpose the matrix like this. You can see here, right? Yeah. Next, what we do is we take output where the torch size is 4 comma 8 comma 16 finally. Then we take a v dot 0. Here we get this part, and this is selected again. You can see it's a gradient or selected backward. Some note you have to remember: What are the nodes you have to remember? Attention is a communication mechanism, can be seen as nodes in directed graph looking at each other and aggregating information with a weighted sum from all nodes that point to them with a data dependent weight. So this is attention. What is attention? Here we have explained. What is self attention? Self attention means, self attention just means that the key and values produced from the same source as queries. In cross attention, the queries still get produced from X, but the keys and values come from some other external source, example and encoder volume. Next, we have a scaled attention. What is scaled attention? Scaled attention additionally divides V by 1 or square root of head size. This makes it so that when input is q comma k, our unit variance V will be the unit variance too, and softmax will stay diffuse, not saturated too much. As we can say illustration below, you can see this illustration, right? Now let's take an example, like we have a French to English translation example. Encode, decode. This is the French, right? This is the French one that says les reacts the neurons sont genax, and we start the decode part that says neural networks are awesome. This is what we are going to do basically. This is the full-fledged code. Whatever we did here, first we do the hyperparameters, and then this is the class head module, one head of self attention, and this is the multiple head of self attention, and this is simple linear layer followed by non-linearity. This is the transformer block, communication followed by computation, and this is the super simple bigram model, that is the bigram GPT, right? So here's the bigram model GPT. I have shown you, I have explained each and every code of it, and now we generate the model and get the decode part. So how many parameters we have here? Just 0.29729 million parameters is taken by this, and these are the steps. That's almost like how many parameters we had. So we took a 5,000 steps, which has a maximum loss of 1.8. So yeah, that's fine. Now what does this do? So this input text has the first 1,000 text in an English word, and this gets converted into, we can say, what did we do? Sorry, I just forgot. Yeah, so what would we do? We just converted it into a French, right? We took a French to English translation example. This is an English text and we converted it into a French text, as you can see over here. Now this was all about the model done by Android sir. Now let me show you the additions that I have done to this model. So what are the additions I have done to this model? First is the bigram model which I made, right? So let's go. Yeah, so I'll just show you the output part, what all we got in the output part. This is the input which we downloaded from the kaggle sorry, from the GitHub repo. So you can see it's in English, right? Everything is in English. I say on to you, everything is in English language. And this is the model, pickle model, which I have made. So you can use this pickle model anywhere, you can implement it, and you will get the desired output of this. Like if you implement web app anywhere you want to, this is the mode.txt file that is available, which we downloaded. Now let me show you my code of what which I have added extra to it. So I have added, basically first is my GPT model, right? Let me show you my GPT model. Yeah, where is it? Yeah, this is my GPT model. You can see this is my GPT model of mine. So you can see here I have done all same hyperparameters, but there are some changes. Here I have taken the batch as a 64, 256 as the block size, and 5,000 as the maximum iteration. And eval iteration interval I have taken as 500, learning rate as 3e minus 4, and this is what these are the same as we saw. And where is the, this is the multi-head attention, this is the feed forward, this is the block, and this is the GPT language model which I have made. So this is the GPT language model. Here I have done self token, self position embedding table, self block, self len, and self lm head with some sequentials embedding of vocab size and n slash embed. Similarly, I have done this is the GPT model, and this is the model GPT language model. Here I have taken a parameter of 10 million parameters. Can you understand? Which we saw the Bigram model, it had a parameter of just 0.209729 million parameters. But my GPT model, which I have made, has a parameter of 10 million. Can you believe it? It's a 10 million parameters. So you can just know that how much time will it take to load, right? So here we can see, which we thank they shall follow men that bear this, that, this. So this is the GPT model output. Now I want to take a output of the more.txt file which I have loaded. So for that, what I do, I print the decode m generate context of Maxwell, and then I get the more.txt file output, which is this. This is basically a dialogue, right? So yeah, see, you can see this dialogue and then this one. So it is a vast difference. And also you can go up and see the Bigram model, which had just 0.2 million parameters, whereas this as GPT model of mine has a much more, like 10 million parameters. More parameters, the model is more perfect, we can say. So next, let's see the pickle model which I've made. Like, how did I convert this model into pickle file? So model.pickle. So here I load the model from the pickle file. So here is the load, like model.pickle, and then I print the model. So this is the GPT language model which I've converted the GPT language model to a pickle model. Let's see this. So token embedding table, position embedding table, blocks, then multi-head attention, module list, 6 crosshead, linear dropout. This linear is key, this linear is query, and this linear is value, and this is the dropout. Then feed forward, layer norm, block, feed forward, like that. It's like the, like we go till end, and here it ends. Now we have printed the parameters that are in the model, the number of parameters in the model. How many parameters we have? 10 million parameters, as I said you. So this is basically the model, GPT model, which I have made. It is similar to the Bigram model, but addition to it, I have given more number of parameters to it. Like I've given a 10 million parameters to it, whereas in the Bigram model there was just 0.27 parameters. So let me conclude this video. I think it has gone too long. So the GPT model, I hope you understood the GPT model. You can see the difference between the Bigram model and the GPT model from here, right? So what is the basic difference? You can see the batch size is just 16 over here and the block size is 32, whereas in my GPT model the batch size is 64 and the block size is 256, which makes the model more stronger than the before one and the output more stronger than the before one. Now similarly, this is just a Bigram GPT model. You can also see his Nano GPT model. Like this is his Nano GPT model. So this Nano GPT model is the simplest and the fastest training medium-sized GPT. It is rewrite of Min GPT that parrot. So this is basically a GPT-2 model of Nano GPT, which has around 124 million parameters. Oh, and this is the validation and lossing and how to install. We can see this repository of him. I will just in the description I will be providing the Kaggle link of my Bigram GPT model, and also I will be providing the GitHub repository of it, and also the collab link of his, like Android source video link I will also be providing in the description. I hope so you liked my video, and if you liked it, please give a thumbs up, and a sub to my channel would be great. And also like, share, subscribe, and modernize AI. So AI is the future, right? So yeah, I forgot to show one difference. Like this one, this is a GPT 3.5 which we use, basically Chat GPT. So how I have written something like this to it, it gives here like this, right? But in our output, how does the output is given? Whenever we give input to it, it will give an output like this. That's the difference. That's it from my side. I hope you liked the video, and yeah, again a special thanks to him. Subscribe the channel, and great going. So here I would conclude my video. Thank you. Have a great day.
sound right, boy.